Can people hear me? Okay. Toby, can you hear me? Oh.
Yeah.
Okay, perfect. Okay, so I've made you host, but there's two of you. So you might need to switch host.
Okay. I'll have a look, see if it works.
Okay.
It seems that I can share screen.
Okay.
Okay, should I get started?
Yes, please. Yes.
Okay.
It's yes, Toby is the author of several assignments for COMPOS, and today Toby is your lecturer. So thank you, and I'll leave it to you.
Thank you. Okay. So today we're looking through Newton's laws and some kind of simple applications of them. So we'll start off by looking at the first law. So the first law is if we're in an inertial frame, an object at rest remains at rest. Or an object remains in uniform motion, so that's same velocity, so same speed and in the same direction. And this holds as long as no forces are applied. And then the second and third law look at what happens when forces are applied. Okay. So the first question is, so you're standing on the equator and you feel the wind blow directly north. If you were to then travel north from the equator, what direction would the wind appear to be blowing in? So the thing, if you're at the equator, so if you're here, in order for the wind to be blowing directly north, it has to be traveling along the surface of the Earth. So the wind has to be traveling along with the rotation of the Earth. And because of the shape of the Earth, the equator spins fastest. So that's just because of the shape. Like if you have a spinning disk, the outside of the disk spins much quicker than the inside of the disk. And so if the wind, as we go up, so we're here, the wind that appeared, and it's important that it appears to be going, directly north from the equator. But remember, in order for it to appear to be going directly north, it has to actually be traveling with the surface of the Earth. And so, as we go further and further north, the Earth gets smaller and smaller. And so, the surface of the Earth is moving less slowly. And therefore, the wind, which comes from the equator, still has the inertia it had then. So it starts off, the wind from the equator is spinning at the fastest it can, because it's at the biggest point or the widest point of the Earth. So it's going around the Earth at its fastest possible speed. So as you go north, as the wind blows north, it's still got that inertia, so it's still moving east in that with that velocity. So actually what we're going to see is the wind is moving faster than the Earth. And so the wind will actually appear to be blowing northeast. So as we go north, Earth, so the speed of the surface of the Earth slows down. And with that, but the wind has same velocity as it did at the equator. And therefore, wind is moving faster the Earth's surface. So it blows, or appears to blow, kind of northeast. The further up you go, the more east that will appear. And if you just go a little bit up from the equator, it will still essentially be north with a little bit of an easterly wind. Does this make sense? This is maybe difficult to picture. So as we went further and further to the North Pole, let's have a think. It's hard to say because the Earth turns away from you. Okay, so if we just had the same velocity, what is north to the equator is directly up when we're at the North Pole. So as we get further and further away from the equator, the wind would appear to be going more and more up. So it wouldn't just be going east; it would be kind of going up north and east as we go further and further towards the North Pole. And obviously, other effects take over. It wouldn't be 100% east. It would just be kind of off the surface. Does that make sense? That's a good question. Are there any others? What's the question? You're right. So yeah, so the question is, some diagrams of the Coriolis effect, you end up with kind of these spirals in the northern and southern hemisphere in different directions. So, I mean, I think you're right that anything that was going completely parallel to the Earth's surface wouldn't be affected, but that's never going to be the case. You're going to have some wind going north and some wind going south, and even wind that's going from a higher up in the atmosphere, but because it's further away, it's spinning faster, which then, as it becomes lower and lower to the Earth's surface, will be then traveling in an kind of easterly direction in the northern hemisphere. So those diagrams you see of the Coriolis effect, where it's looping, kind of include more than just this effect. Okay. We go on to question 2. What force is acting on you as you sit in this chair watching this webinar? So let's have a look. There's, well, this person, they've got their feet on the ground. Okay, well, the most obvious one is gravity. So let's start there. They've got gravity, or their weight. So the weight equals their mass times the gravity. And then you have a reaction force coming from the ground if your feet are on the ground. Let's call this R ground. And another reaction force coming from the chair. So R chair. And for this person, also the force from the phone, but we'll ignore that. There is, however, maybe one more, which is very maybe easy to miss and one that doesn't really come up in problems that often. But there's also air pressure. So there's air pressure from the outside. Coming in, but then there's also air inside you, which pushes outwards. So there's force from the air outside and the air inside. And these cancel out. So the main ones are going to be your weight and then the reaction force from the chair and the ground. Does that make sense? Okay. We'll move on to section 2, where we're looking at the frictionless motion, or often some of these problems, there's no motion going on. So the acceleration is 0 and all the forces balance. But either way, this whole section, there'll be no friction. So let's look at question 3. There's a tightrope walker weighing 70 kilograms, is in the middle of a tightrope, and under their weight, the rope sags slightly. So it makes an angle of 5 degrees with the horizontal. What is the tension in the rope? So the tension is going to be the same on both sides. And also, the tension in the rope must create enough upwards force to counteract the weight of the tightrope walker. So let's zoom in. What do we have? Let's zoom in on the tightrope walker and draw a free body diagram. We have the weight is equal to 70 G. And then we have the two forces from the tension of the rope. And these are both at 5 degrees to the horizontal. Now, what we want is the component of the tension in the vertical direction, because we need it to balance the weight. So in order to get the vertical component of the tension degrees, we can use trigonometry, where the vertical component here is the opposite. And the tension is the hypotenuse. So we have the vertical component is, let's call it T vert equals the tension times sine of 5 degrees. Okay, and now we need we need the vertical components of tension to balance out the weight. So the weight equals 2 times T vert. And the reason it's 2 is because we're getting the force from both sides of the tightrope walker. So we put this in and we have 2t sine 5, which we can rearrange to get t equals w over 2 sine 5, which we can then plug numbers in. So the weight is 70 kilograms times 9.81 meters per second squared. And then 2 times sine 5, which is, if I type this into my calculator correctly, 3,900 newtons. Okay, are there any questions here? Okay. Okay, so let's look at question 4. So we have a pulley system, and we want to find the initial acceleration of both these masses. So let's look at the forces. So firstly, there's going to be tension in the rope. And this tension, because it's just one piece of string, one piece of cord, the tension is going to be the same throughout the string. So the tension's the same everywhere. So let's look at the net force on M2 to start with. So we have the force down is equal to m2 times g, and the force up is the tension, and this equals the acceleration, or mass times acceleration, was m2a. And I've picked down equals positive. You could, of course, done this the other way. And similarly, if we look at m1, the weight down is m1g, and the force up, well, this one here is being held up by two pieces of the rope. So actually, the weight up, so the force up, is 2t. And this is equal to mass times acceleration, which is m1a. Or let's label these a2 and a1. So they're the acceleration of mass 2 and mass 1. Okay. There's one more thing we need. So here, we don't know what the tension is. So if we want to solve this for the acceleration, we currently have two equations, but three unknowns. The arrow up for the tension in the middle. Do you mean here on the rope? Yes. So you're right. So if you have a string in a piece of rope, at any given point, there's tensions working either side of it, pulling it. I mean, do I have a piece of... I've got a Christmas decoration that's got string on it. So, as we stretch this, at every given point, I don't know if you can see this, it might be a bit blurry, but as I pull this, at every little point, it's getting stretched a bit to the right and a bit to the left. So the tension always acts in both directions. Does that make sense? Okay. So finally, we need to, since we've got three unknowns, which is the tension and the two different accelerations, but so far we only have two equations. So in order to solve these, we need one more equation. And what we can actually relate is the two different accelerations. So if m2 were to rise a little bit, we find that m1 would fall down only half that amount. This might be hard to see, but if m2 were to rise, say, a distance x up, then that distance, and as that goes up, m2 comes down. It's only a fixed length of rope. And this would move down x over 2, such that when you add up the amount the cord or the string has increased either side of the pulley that m1 is attached to, that extra length must equal the distance m2 has moved. So this gives us the acceleration of m2 equals -2 times the acceleration of m1. And it's negative because as m2 moves up, mass 1 moves down. Okay. Now we need to work out the acceleration. And there's going to be a fair amount of algebra. So we can firstly rearrange this equation to get A2 equals T minus M2G all over M2, which is equal to T over M2 take away G. And we can rearrange this one to get A1 equals 2T over M1 take away G. Okay. It's an easy way to do this. Let's have a look. Now, using this extra equation, we can also say that A1 is equal to G over 2 take away T over 2 M2. How did I solve this? I've got it written down, but now I can't read my handwriting. So we can rearrange this to get 4 M2 A1 M1 equals 2 M2 G over M1 take away 2T M1. Now that may seem like a weird step, but now what we can do, if we do A1 add 4M2 M1, we get sorry, I do apologize. I think my work I've written down is slightly wrong. I don't want to lie to you. Becomes 2T over M1, take away G, add M2, M1, yes, no, this is correct. Take away T over 2. Okay, yes, that's a good question. How can M1 accelerate if it's just hanging from the pulley? You're right, but the pulley itself can move down. So the pulley is held up by the string which is attached to M2. And so, yeah, as M2 goes up, you're right, the distance between M1 and the pulley doesn't change, but the pulley itself goes down. Okay. And then what we can see is that, so that should be over. G minus 2t over M1. So what I've done is I've added A1 in the form of this. And then what I wanted to do was cancel out. So I created this here, which is maybe quite complicated. But what's important is that here, the term that includes the tension is the opposite of the term that includes the tension here. Okay, so that means that this term here cancels with this term here. And we can simplify this whole thing to be A1 times 1 plus 4M2 over M1 equals G 2M2 over M1, take away 1. Which gets A1 equals G 2M2 over M1, take away 1, over 1 plus 4 M2 over M1, which we can simplify this slightly as G times 2 M2 minus M1, with that over M1 plus 4 M2. And then finally, to get A2, we said was negative 2 times A1, we end up with, well, we can just put the minus 2 in front. And then we can maybe simplify this slightly. G, well, I've taken the minus sign here, and I've used it to swap the signs in the numerator up here. Okay. And then finally, for part B, let's go back up. It said find the relationship between the masses such that the system remains stationary. So for it to remain stationary, we have A1 equals A2 equals 0. So when do these equal 0? This will happen when M2 equals M1 over 2. So I did that. I maybe skipped a step there. So look, when this is equal to 0, I'll go back. Yeah, so I did skip a little bit there. Let's have a look. We have 2G M1 minus 2M2 over M1 plus 4M2 equals 0. So when does this equal 0? Well, G is positive, so we can ignore that. The denominator, that's positive, so that's never 0. So we need the numerator to be 0. So we need M1 minus 2 m2 to equal 0, which is m1 equals 2m2, or equivalently, m2 equals m1 over 2. And then this tells us why these kind of pulleys are useful. So you see that this is stationary if m2 is half the mass of m1. So what this means is if you want to pull m1 up and raise it up, and you only need to give a force that's equal to half of its weight. And that's why these kind of pulleys are useful. Does that make sense? Or do people want me to go through any steps of this again? There was quite a lot of algebra. Oh, I got. So someone's asked. So from where the red arrow is to the line below it. So here we got from saying A1 is minus a half A2. To get to the line below it, well, I just lost it. Yeah, so to get to, you're after, I'll use a different color, this line here. So you're right, it is a bit of a trick. Why did I decide that 4m2 a1 over m1 is the important quantity to look at? Well, I wanted to get rid of the tension, right? The question never asked for the tension. You could sit there and work it out, and that's fine, but it might be better to work out a way of creating a quantity that ignores it completely. And what I wanted to do, so to find a way to make the tension cancel, what I wanted to do is to find a quantity where this term and whatever happens with this term could cancel. So we see that if I times this here by 4m2 over m1, I get minus 2t over m1, which is exactly what I would need for it to cancel the term with the tension on the other side. And so the reason I times this whole thing by 4m2 over m1 is so that the tensions cancel. So when I add a1 with this new quantity, the two terms with the tension cancel out and we can ignore it from then on. There are, of course, loads of ways to solve this. Lots of them, however, will involve finding the tension. And there might be more obvious, but it would require a lot more steps. Okay. Okay, for the final section, let's talk about friction. So, if something's resting on a surface, it's got its weight, but the force coming back from the surface is the normal reaction force, or the reaction force from the surface. And now, from Newton's third law, and a common mistake, is that the reaction force from the table is not the equal and opposite force accompanying the weight, right? The weight comes from gravity. And so the equal and opposite force for the weight, well, the block or whatever it is pulling back on the earth. with gravity. Whereas the interaction force between whatever the block you have and the table is actually caused by an electric forces. And so there's a reaction force from the table, but the table also has a reaction force from the block itself. And it's this reaction force that determines friction. So, I mean, you've seen this. If two things are barely touching, there's no force between them, then they can just slide right past each other. Even if they could be really rough, sticky objects. If there's no force between them, they can just slide right past each other. Alternatively, if you have loads of force pushing between two things, even if they were potentially quite smooth, you'd have a hard time getting them to slip past each other. So, friction is equal to the reaction force, we call it R, times what's called the coefficient of friction. And this just tells you about the material. So the higher the coefficient of friction, the harder it is to slide past. Now, there is a difference between what's called kinetic friction or dynamic friction versus static friction. So for kinetic or dynamic friction, this is when things are actually moving. Well, actually there. So this is the friction when things are actually sliding past each other. Alternatively, when things are stationary, friction works a bit differently. This is called static friction because things are static. So, firstly, the coefficient of friction is actually quite often a bit higher. And secondly, the friction force, so the friction reaction force times mu, that's actually the maximum possible force the maximum possible friction force. If I'm not sliding my hands past each other, or not even attempting to, they're just pressed against each other, there's no friction force here. They're not trying to slide at all. If, however, and you probably won't be able to see this, you'll have to take my word for it, I attempt to push my right hand up and pull my left hand down. If I attempt a little bit, they're still not sliding. There is a small friction force that cancels out the force from my arms trying to slide my hands. Then, as I increase the force, so I try harder and harder to slide my right hand up and my left hand down, they're still not moving. The friction force between them has increased, and then they start moving when the force I'm putting in my arms is bigger than this force of static friction. So I'll write that down. So for static friction, we have the friction force is always less than the reaction force times mu, so the coefficient of static friction. And there's always less. Or rather, less than or equal to. When they're equal is when things are just about to slip. You know, they're teetering on the edge. A tiny little bit more force and you're going to slip. So when the friction force is equal to mu r is when things are just about to slip. When things are sliding, the friction force is always equal to mu r, but in that case, the mu is the dynamic or kinetic coefficient of friction. And finally, it is often the case that mu static is greater than mu dynamic. So we see this as things start to slip. You're going to take a lot of effort to slide things past, to get things going. But once they've started moving, they can whiz really easily with very little force. And this is why the coefficient of static friction is often bigger than the coefficient of dynamic friction. Okay, are there any questions? There's maybe quite a lot. Okay. Let's have a look at question 5. So, a toy catapult works in the following way. So a load or an object is placed into some tracks, and it's attached to an elastic band. As you pull it back, the elastic band stretches such that when you let go, the load flings off. When this is relaxed, so if you look at the picture, when this is relaxed, or in its kind of default before it's been stretched back, we see that the elastic band has length L, and as we pull it back, it gets stretched. And just to make the algebra nice and easy, or as easy as it can be, this is quite a long question. The coefficient of friction, I've just said, is 1. Let's make things easier. And okay, so let's work out the acceleration of the mass. So let's draw a free body diagram for the mass in the tracks. So here it is. What do we have? We have its weight. I forgot. Oh, no, I did say mass. It has mass m. So we have weight, which is equal to mg. There is some friction force, which is equal to mu times the reaction force. There is a reaction force coming from the tracks. And also, there is this tension force coming from the elastic band. So there's quite a lot of forces we need to look at here. Maybe let's start with the elastic band. Of course, start with any of them. Let's start with the elastic band. The length of the elastic band, after it's been stretched, we can use Pythagoras' theorem for. So the length of the elastic band is the square root of x squared plus L squared. However, that doesn't tell us how much it's been stretched by. I think an elastic band, when it's completely unstretched, still has a length, and that length was L. So the amount it's been stretched is square root of x squared plus L squared. Take away the initial length. And the tension in this is equal to K times the extension, which is equal to K times x squared plus L squared, take away L. Now this is acting both forwards and down. So we want to split this up into the forwards component and the downwards component. So let's say it makes an angle theta. And we'll see that there is a trick for working out theta. So let's look at the force in the forwards direction. We have T cos theta. But we don't know what theta is. However, we can look at this triangle and we could work it out from the distances given. However, we don't actually ever have to work out theta directly. We can just look at cos theta and sine theta and work those out, what we have. They end up much easier to work out. So, cos theta equals adjacent over hypotenuse. If we look at this diagram, if we zoom in, the adjacent is x, and the hypotenuse, which was here, is the square root of x squared plus L squared. So cos theta is equal to the adjacent x divided by the square root of x squared plus L squared. So if we put all of this in, we have T cos theta equals, so firstly we sub in for T is equal to K times the square root of x squared plus L squared minus L. So that's T times, I'll put a little times there so we just remember they're different, times cos theta, which is x over the square root of x squared plus L squared, which we can simplify this slightly and we get kx 1 minus L over the square root of x squared plus L squared. Okay, now let's look at the downwards force. Now the downwards force is going to be needed to work out the reaction force, which we need to work out the friction. So let's look at the downwards version of this, or the downwards component of the tension rather. And we have, this is equal to T sine theta. And again, we can do a similar trick for sine theta. This is equal to opposite over the hypotenuse. We scroll back up to the diagram. The opposite, so yeah, someone's just asked the last step into kx. So to get from this last equal sign, I have just, so I've taken this x and I've moved it to the front. And then I have put this of that. I'll do a couple of steps so we can see it all. Okay. This is equal to kx times this. Okay, yes. And then I multiply the brackets with this fraction here. So we have kx times the square root of x squared plus L squared, square root of x squared plus L squared, minus L over the square root of x squared plus L squared equal to kx. Well, these cancel and we just get 1 minus L over. Okay, let's go back. So in order to calculate sine theta, we do opposite over hypotenuse, and the opposite is L. So this gives us L over the square root of x squared plus L squared. And so getting t sine theta, that gives us, back in for t, we had k times square root of x squared plus L squared minus L times L over the square root of x squared plus L squared, which we can simplify in the exact same way as above, which gets KL 1 minus L over x squared plus L squared. Okay. So in order to work out the acceleration, we need to work out the net force in the horizontal direction. So in order to work this out, we've already worked out the force to the left, which is t cos theta, but we need to work out the friction force. And in order to work out the friction force, we need to work out the reaction force. So the reaction force this cancels both the weight of the object and the force from the elastic band pulling it into the tracks. So R equals mg plus t sine theta, which equals mg plus KL 1 minus L over the square root of x squared plus L squared. Okay. This means that the friction force is equal to mu R, but I've already said in the question, let's set mu to 1. So that's just equal to the reaction force. So the net force forwards is equal to the force pulling it forward from the elastic band. We've already said is kx 1 minus L over x squared plus L squared take away the friction force, which we take away mg, take away KL 1 minus L, the square root x squared plus L squared, which can be simplified slightly. Still not exactly nice, but we see that this bracket here is the same as this bracket. So we can simplify this slightly to K x take away L 1 minus L over the square root x squared plus L squared minus mg. And then the acceleration A equals the net force divided by the mass, which equals K over M minus L 1 minus L square root of x squared plus L squared minus mg. Oh, not mg, we've divided that by m, so the m's cancel. Some of these statics questions do have a lot of algebra, but you can see that if we do them step by step and work it out carefully, we do get there in the end. So are there any questions, or are we happy to move on? Okay. Let's look at this. So a block is held. So a block of mass m is on a 45-degree incline. So I'll write that in here. 45 degrees. And it's held in place by a spring with spring constant K. What are the minimum and maximum values for the extension of the spring such that the block doesn't move? And the coefficient of friction between the block and the slope is mu. So there are two possible ways this could be. So firstly, if the spring is only stretched a little bit, we'd have the weight always has a component down the slope. And in the minimum case, we'd have the tension pulling it up and friction pulling it back up. Or rather, not pulling it back up, but stopping it slide. Alternatively, what we could have is this really stretched. The block would still, under its own weight, want to slide down. The tension in the spring will be pulling it back up, but it's been so stretched that if it wasn't for friction, it would just spring back up. So actually, friction is stopping it being pulled back up. So the friction also acts in the downwards direction. And remember that this is going to be static friction, right? At the minimum and maximum extensions, things still aren't moving, but it's about to start moving, right? If we were to extend this any more or any less, everything would start moving. So we have the friction force is equal to mu times the reaction force. And that's because we're just at the very edge of slipping. If this was stretched somewhere in between minimum and maximum, then the friction force might be much less. And in fact, there is a point in between these where the object sliding down under its own weight and the force of the spring back up completely cancel. So, and in that case, there would be no friction at all, because it's not moving and it's not even about attempting to move. So, let's look at forces in the direction parallel and perpendicular to the slope. So, the weight of the block, so here's our block. So we have weight, and we can split this up into parallel and perpendicular components. So the parallel component in this direction is mg cos 45 degrees. And in the perpendicular direction, so this is the force into the slope, here we have mg sine 45. Now, cos and sine of 45 degrees are exactly the same. So both of these are equal to mg over root 2. And so this means the friction force. So firstly, this means that the reaction force coming from the slope. So if we look here, the block can only slide parallel to the surface of the slope. It can never move into the slope. And so therefore, the reaction force in this direction must be equal to the weight, the component of the weight in that direction. So here I'll say is equal to the reaction force. So the friction force is equal to mu r, which is equal to mg over root 2 times mu. So let's look at the minimum extension it can have. So the minimum extension it can have is when the tension and the friction acting in the same direction. So we have T plus friction equals the component of the weight down the slope, which is mg over root 2. And that happens, and we've already said friction is mu mg over root 2. And we want the extension. So T equals kx. So we have kx min, this is the minimum extension, plus mu mg for root 2 equals mg over root 2. And we can rearrange this to get x min equals mg over root 2k 1 take away mu. And so if the coefficient of friction is equal to 1, so mu equals 1, then actually this will never slip down the slope of its own accord, no matter how, even if there was no spring there. Now, alternatively, The maximum extension it can have is when tension acts in the opposite direction to both friction and the component of the weight down the slope. So tension is equal to friction plus mg over root 2, which is equal to mu mg over root 2 plus mg over root 2, mg over root 2, 1 plus mu this time. And again, T equals Kx. We have this is equal to Kx maximum this time. So we have X max equals mg over K root 2, 1 plus mu. Okay, are there any questions, or are we happy to move on to the final question? I understand these friction questions can be can involve quite a lot of steps. Okay. So here we've got a slope. So let's say you have a shelf and you've got two copies of the same book on top of each other, but the shelf is broken and slipped down to the side, and these books may or may not slip down. So they're both the same book, so they both have the same mass m. The coefficient of friction between the book and the shelf is mu1, and the coefficient of friction between the books is mu2. So which book will slip first? In other words, if the bottom book slips first, then what we're going to have is both books sliding together. If the top book slips first, then that book is going to fall off the top book. Oh, sorry, the top book is going to fall off the bottom book, and we'll end up with two books next to each other. So, and again, we're looking at the limit of which one's going to slip first. And so we're going to have friction equals mu r, because at the limit of slipping. And finally, how do we work out which one slips first? Because you either work out if they slip or they don't. So, how do we interpret which book slips first? Well, this depends on the angle. So if it was, obviously it's a completely flat shelf, neither will slip. If the shelf goes like this, well, they're both just going to fall off. If what's going to happen is the shelf, when I say slip first, the way to understand this is as the angle gets steeper and steeper, which book will go first? So in other words, which book will slip at the smallest angle? So let's look at both books individually and see at what angle they can slip for. So let's look at the top book. What do we have on it? We have its weight going this way. We have a reaction force coming from the other book. We have friction, which is equal to mu2 times the reaction force. And this weight here can be split up into parallel and perpendicular components. So to split this up, we notice that this angle here is theta. Now you can see that's through similar triangles. The way I often do it, or at least to check, which of these angles is it going to be the red angle or the green angle? That's theta, that's the angle given here. Now the way I do it, or at least a trick I have to check, is I look at if this shelf, if theta were to go to 0, so this were to be completely flat, would all of the weight be parallel or perpendicular to the shelf? Well, all of the weight would be perpendicular. It would be directly into the shelf. And so as theta goes to 0, so the shelf comes completely flat, this red angle here would also go to 0 because the weight would go directly through the shelf. And so it's the red angle that is theta, not the green one. So let's look at the two components. This here, in this direction, we see that the perpendicular length is the adjacent. So this is W cos theta. And down the slope, in the parallel direction, we have W sine theta. So this means the reaction force is also going to be equal to W cos theta. So let's look at the net force down the slope. This is the force down the slope is the weight acting in that direction, which is mg sine theta. Take away the friction force is what's pulling it, or not pulling it back up, but stopping it slide down. So that is mu2 times W cos theta, which is mg cos theta. And when this is on the very edge of slipping, this is equal to 0. So we can work out the angle at which this flips. So we want to get the thetas on one side and everything else on the other side. So we start off by adding this, the second term, to the other side. So we have mg sine theta equals mu2 mg cos theta. And then, well, we can cancel these mg's from both sides. So we have sine theta equals mu2 cos theta. If we now divide by cos theta, we have sine theta over cos theta, which is equal to tan theta, and that is equal to mu2. So we'll see that we don't need to work this out anymore. We haven't been given numbers. So we can't work out what theta is as a number. We're just going to have to leave it as tan theta. And then at the end, use the properties of tan theta to try and work out which angle is bigger, even if we can't get an actual number. So let's look at the bottom book. So again, it's got its weight down. But actually, It also has the reaction force coming from the top book, right? The top book is resting on it. So it's got its own weight pulling it down. It's got the reaction force from the top book. It's got its own friction between it and the ramp. It's got its own reaction force holding it up from the ramp. And then there's also friction from the top book, which the top book is sliding down. The friction from the top book is going to act in this direction. Okay. This one's quite complicated. Well, bits of it we've already seen, but there's just a lot of things going on. So let's look at the reaction force. So the reaction force coming from the ramp this has to balance, firstly, the weight, or the component of the weight that goes into the shelf, which we saw was W cos theta, but it also has to balance the reaction force coming from the top book. So if we combine both of these, W is mg cos theta, and R from the top book is also, where is it? Mg cos theta. This is equal to 2 mg cos theta, which makes sense, right? The shelf has to balance the weight of two books, not just one. So friction from the ramp then is equal to R ramp times mu1, which is equal to 2 mg mu1 cos theta. The friction from the top book, what pulls it down the slope, is exactly the same as the friction force stopping the top book sliding down, right, from Newton's third law. So this must also equal, where is it? Mu2 mg cos theta. So let's look at the total force. The force. Firstly, we have the force down the slope from its own weight. And we also have the friction of the top book pulling it down. And then stopping it slide down is the friction from the ramp. So this is 2 mg mu1 theta. And if it's just about to slip, then this is equal to 0. If this is greater than 0, then it will be sliding. If it's less than, well, the maximum it can, the smallest amount it can be is 0. It's less than 0, it'll be sliding back up. But actually, with friction, if it was less than 0, then the friction would be less than the friction I've written. Because static friction, if something's not attempting to slide at all, or anything's making it slide, static friction is just 0. So this here, at slip, when it's about to slip, this is 0. So how can we simplify this? Well, we can cancel all these mg's, and we can make the two cos theta terms one term. So we have sine theta, take away 2 mu1 minus mu2 cos theta equals 0. And this is a very similar expression to, where is it? The one we have here in the middle of the screen now. So we do the same kind of thing. We bring this to the other side. We have sine theta equals 2 mu1 minus mu2 cos theta. So dividing by cos theta, we have tan theta equals 2. Oh, sorry, the 2 should be inside the brackets. Equals 2 mu1 take away mu2. So, which of these slips first? So, the angle at which the top book slips is tan theta equals, where did I put it? Mu2. And the angle at which the bottom book slips is 2 mu1 minus mu2. Okay. Then, in order to work out which of these angles is bigger, we don't know any numbers. If I told you mu1 and mu2, you could just put this in and see. But I haven't told you any numbers. And so we're going to have to use our understanding or our knowledge of the tan graph to know or try and deduce which this is. So if we plot tan theta against theta, we have, well, this here is 90 degrees. We see it goes like this, where it goes off to infinity here. 90 degrees. In other words, as theta gets bigger, tan theta gets bigger. So we need to work out which of these is biggest. And that depends, firstly, on the values of mu1 and mu2. If mu1 equals mu2, so the coefficient of friction between the books was the same as the coefficient of friction between the book and the ramp, then they would start slipping at the same time. If mu1 is much, much bigger than mu2, then there's a lot of friction between the book and the shelf, but not much friction between the two books themselves. Then the top book will slip first. If, however, mu2 is greater than mu1, in other words, the books are very sticky between each other, but there isn't much friction between the book and the shelf, then the bottom book will slip first. In that case, the books kind of just slip together. All right, does that make sense? These last few questions were quite long and took a lot of algebra. But are there any questions? Okay. Well, that's all I have planned. So unless there's any questions, I think you're free to go and have a nice evening.
Thank you so much, Toby. See you everyone next week.